Right, good afternoon, everyone.
Good afternoon.
How did the homework go? Did you guys do them?
We've been doing it.
Any questions? Can you please put them on the chat so we can discuss them? Bryce, number 26. Okay. Any question beside 26? All right, so we group 26. So this is my situation. Okay. Before I do 26, actually this will guide us to number 26, I would like to make a note that I tried to make it a point that I tried it at the end of the lecture last time, but now we have to repeat. So let us make this note, which is actually important. We're going to use it. The idea that suppose I have a matrix A, and I reduce it, and you get U. So U is basically the echelon form of A. Okay. If I take A, I take the augmented matrix A and I perform operation on it, so it's the same A. Then if I perform the operation, I usually end up with the U and another vector D. So let me explain what I am talking about. So I'm going to take very simple example. So suppose A is the following matrix: 1, 2, 3, 2, 1, 2, for example. And let us say this is 0, 0. So I take the matrix A 0. And let us say I perform operation to get to the echelon form. So I pick a problem where I don't have to do a lot, just to show you the idea. So I will take minus 2R1 plus R2, and this will become my new R2. So this will be, of course, a 0 because it's 0, and this will become 0 here, and this will become minus 3, and this will become minus 6 plus 2, minus 4, and this is 0. This is the U I am talking about. Okay. Now, if instead of 0, I solve, for example, AB. Okay, I have AB. And let me make up something. So it's the same A, but here I have an augmented term. Let us say 4. It doesn't matter what I'm going to put. It is not relevant. 2, 1, 2, and let me put a 2 in here. Now, if I want to reduce, will I do the same operation as here? Will the same operation have to go, or I change the operation? The augmented term is at the end. So all the operation I'm going to do now are the same operation, even if I did not have the A, even if I did not have the B. So it's the last term which is going to be affected. So it means that if I do the operation here, I'm going to do the exact same one. I'm not really going to change. And this will get me 1, 2, 3, 4. And I'm going to get exactly that. The only thing which is changing is the augmented term. So now this will become minus 8 plus 2, which is a minus 6. Right? So this is an idea that I will come back to it. So if you take a matrix A, you reduce it, you get U. When you add the term, when you augment it, and you start working on it, you're going to end up with the same U, but this term will change because this augmented term is actually changing, and that's what I am calling it a D. Why is this relevant to number 26 and how to understand number 26? So let me read 26 very carefully, and then I will let you figure it out. Number 26 tells me the following. Suppose AX equal B has a solution. So I have a system, and we're going to suppose that AX equal to B. It means when I solve this system has a solution. So suppose this is given. This is consistent. Explain why the solution is unique precisely when AX equal to 0 has only the trivial solution. So what I want me to show is that to explain why if AX equal to 0 has only means has only the trivial solution, then Ax equal to B has a unique solution. Okay. So that's really the question. Why, if Ax equal to 0 has only the trivial, then if I plug in the B, I will have only one solution. Who can provide us with an explanation of why this is the case? So why this information about A, X equal to 0, about the homogeneous, will help me to make, granting consistency, a good explanation for Ax equal to B. Anybody have any idea what's the picture in here? What's the picture? Anyone? Okay, if Ax equals 0 has only the trivial solution. Remember, the trivial solution, it means a solution which is x1 equal x2 equal x3 equal to 0. So it has one solution. What does this tells you about the echelon form of, so suppose Ax equal to 0 has a unique solution, only one. What does this tell you about the echelon form of U? Suppose U is the echelon form of A. So let's play again. Let's take A, for example, 4 by 3 matrix. Let's take it to be 4 by 3. If Ax equals 0 has a unique solution, one solution, means when I solve, that's 4, 1, 2, 3, the system 4 equation and 3 unknown. 1, 2, 3, 4, 1, 2, 3, and Ax equal to 0. So if I solve, if this has a unique solution, how does the echelon form look like? What can we say about that? Every column has a leading, and that's crucial. I will have a leading here, I have a leading here, I have a leading here, and this row has to be all bunch of zeros. So that's how the echelon form would look like. So I'm gonna have a leading, so this is my U. So if U is the echelon form of A, then U has a leading in every column. Otherwise, I will have infinitely many solutions. Okay, there is no free variable, exactly. Why will this affect Ax equal to B? Why then Ax equal to B will have a unique solution? Ax equal to B is consistent. So when I solve the system Ax equal to B, what's gonna be the picture? First the picture and then the logic. Suppose instead of A0, I have AB. Based on what I said a minute ago, if I'm gonna reduce AB, what's gonna happen? What's gonna happen? This piece will be the same as that, and this piece will change. So what's gonna be the scenario? I'm gonna have a leading here, bunch of zeros, because the U is the same. That's what happened to you. I'm gonna have a leading bunch of zeros. I'm gonna have a leading bunch of zeros. What am I gonna have here? This is gonna change. I don't know what. It's not B because I perform. This is gonna change. This is gonna change. What about this one? In this particular scenario, what should it be?
Leading?
What? No?
No.
No, if this is leading, what does this tell me?
Not consistent.
Right. The problem tells me that Ax equal to B is consistent.
It has to be 0.
It has to be 0 because the problem tells me it's consistent. So this has to be 0. So those terms, I don't know what they are. It depends on A, depends on B. Because it's consistent, this has to be 0. And now we can argue how many solutions Ax equal to B has. It has exactly one solution because we have a leading in every column. And definitely there is no leading in the last column because the system is consistent. So there is no room for the free variable. So this information about A helped me to get information about AB, but I needed the fact that it's consistent. Otherwise, I don't know what goes in here. Without the condition of consistency, I don't know what goes. It may be inconsistent, but that's not the case because that's what's given to me. So now we can conclude that since the augmented matrix of AB has a leading in each column, or basically have no free variable in each column, except the last one, the last, because we have consistency, every variable is basic, or there is no free variable. Every variable is basic. There is no free variable, so a solution is unique. No free solution unique. Okay, that's how we kind of think about those problems. We analyze what is really the situation. What is really the situation? Okay. Any other questions about that? About those problems? Just remind you that exam number 1 is next Wednesday, I meant, and everything will be on it. We'll talk about that at the end of the hour. Right? So I'll do one more problem along those lines, and then we proceed. So suppose I assign number 29, for example. I read it, and I want you guys to get me what you think about it. So we have a 3 by 3 matrix, and A has 3 pivots, meaning that for you, a pivot means when you reduce it, you have a lead, you have 3 leadings. It means that when A is reduced, we have 3 leading. Okay. Question is, AX equal to 0. Does it have, is the solution unique? We know there is one solution. The question is solution unique? Question number 1. Yes or no? Is the solution unique? What can you say? So A 3 by 3. I try to solve the system AX equal to 0. So my coefficient matrix have 3 leading, 1 reduced. Is AX equal to 0 has a unique solution? Yes, no, why? Yes, because again, you think about it. You think about it. This is A, this is 0. If it has 3 pivot, it means when you reduce A, of course, when you reduce A, since that's homogeneous, this term is not going to change. It means we have 3 pivot. This is forcing this picture. Means I have A, no basic, every variable is going to be basic. So when I'm going to solve backward, whatever this number is, let us say this is 2. 2x1 equals 0, x1 will be 0. Sorry, 2x3 0, x3 will be 0, back up, x2 will be 0, back up, x1 equal to 0. So definitely solution unique because I have leading in every column. It means no free variable. No free variable. Solution absolutely unique. Yes, now, question number 2 is, if I try to solve the system AX equal to B, and the question is, does AX equal to B has a solution regardless what B is? So if I try to solve AX equal to B, do I always get a solution? Or there are possibilities where we have inconsistency? What can you say? Just imagine the matrix, imagine the scenario. Anybody would like to think? If I put a B in here, do we guarantee you under those conditions that the solution will be there?
Actually, wait, isn't it no because can't you have a inconsistency when the leading entry is in the last column?
Is it possible? Look the echelon form of U, of A. So based on the first remark, that's why I started the remark. If I take A and B and I reduce it, I should get the following. The A, when I reduce the A, even if I have B, the reduction process is the same. So I'm going to end up here with leading, leading, leading. Because I told me we have 3 leading. So the B term is going to change. That's what's going to happen. Is there a room for inconsistency in this scenario? There is no way I can have a pivot here because all the pivots are here. All the leading, I have 3 leading. And we cannot have more than 3 leading because we have 3 rows. So since we have 3 rows, the maximum number of leading is 3. And all those leading are right there. So there is no more room for leading in the last column.
No, what I was saying is in the bottom row, if the leading was in the last column, wouldn't that give you consistency?
It cannot be. We cannot have a leading here. Because the matrix have 3 leadings. The U have 3 leadings, this piece.
Oh, okay, okay.
That's crucial. The A have 3 leading. Are you with me?
Yeah, I
The
understand.
A have this 3 leading. It means when you take A and you manipulate, you're gonna have 3 leading. So all of them has to be to the left of the last column.
Okay.
All the leadings, there is no room for inconsistency in this case, regardless what B is. So now here the system, the answer is X equal to B has a solution for all B. The reason is in this scenario, I would say because there is no row, there is no, since every row of U, the echelon form, has a leading. Every row has a leading of the echelon form. Of the echelon form, it means that no leading in the last column. Since every row has a leading, it means no row of the form, let me write it in an easier way, no row of the form, the following: 0, 0, 0, this way. There is no way I can have the scenario because the echelon part of the coefficient matrix, the echelon part of the coefficient matrix has a pivot in every row. Every row has a pivot. That is, or as a leading, means I cannot have this scenario. It means the system is consistent. All right? So that's how you think about those problems. Very calmly, you think about the scenario. Before I proceed, because we have a lot to talk about today, let us say I make up the scenario where I'm allowing only 2 pivots. It means I have a 3 by 3, but when A is reduced, I have 2 leading. Intuitively, will the system has a solution for all B? You think? So it means when I reduce, I have 3 leading. It means this is the picture. Do we have solution for all B? In this case, the answer is for some we may have and for some we don't, because it's going to depend what we end up with here. If we end up with non-zero, if this B give me a non-zero here, no solution. If this B will give me a 0, that is a solution. So that's really the scenario in this situation. Okay, today we're going to move to section 1.7, absolutely crucial section in linear algebra. And we're going to talk about the idea of linear independence. And the linear independence idea is in a simple word at the beginning. Suppose you have three vectors, v1, v2, and v3 in R3, let us say. Intuitively, we're going to define the following notion. We're going to say that those are linearly independent intuitively if none of them could be obtained by a linear combination of the other. That's really what we would like to get to. So they are linearly independent is there is no way I can write V3 as a linear combination. I cannot write V2 as a linear combination, and I cannot write V1 as a linear combination. So they are intuitively independent from each other in terms of linear combination. That's really the goal, the notion that we're going to define. But the definition is going to take a little bit of a twist before then we come back to what I talked about. So definition. Let V1 through Vp, bunch of vectors in Rn. It means in Rn, it means each one of them has n entries. That's what Rn is. Then we say that the vectors are linearly independent. So we say that the vectors are linearly independent if the only, which is I marked carefully, the only solution to the vector equation x1 v1 plus x2 v2 plus xp vp equal to 0 is the trivial solution. So vectors are said to be linearly independent if the only weight, only zero combination of the vectors is the zero solution. The only way I can put weight here to make this sum 0 is x1 equal x2 equal xp equal to 0. The only solution to that. Now, they are linearly dependent. Linearly dependent. If I can find scalars or weight, not all zeros, some could be, but not all of them, that makes this sum equal to 0. So linearly dependent if I can find a bunch of scalars, not all of them 0, but this sum equal to 0. Independent means the only scalar that make this combination the 0 vector are the 0 scalar. Okay. In other words, so now dependent if this equal to 0 has non-zero solution. In other words, if this vector equation has a non-zero solution. So dependent, independent, it means this vector equation has only the 0 solution. Dependent, it means this vector equation has a non-zero solution. And now let us start understanding those definitions very, very slowly. Okay, shall I move on? All right.
1 second.
Now, there is one more definition that, again, I will make it clear as I work out the problems. The equation x1 v1 plus xv vp equal to 0, that is obtained. So suppose we solve this and we get non-zero solution. The equation obtained by substituting the non-zero weight is called the linear dependence relation among the vectors. Means if the vector, I can find scalars not 0 that make this combination 0. If I plug them back into this equation, what we get is called the linear dependence relation among the vectors. And now let us start understanding those definitions. Okay, so my first example is, these are 3 vectors in R3. And the question is, show that they are linearly independent. So what does it mean, show that they are linearly independent? It means we have to show that. That's what we have to show. That the following equation, x1 v1, because I'm telling you, show that they are linearly independent, means I have to show you that the only solution, to this equation, so it means this equation equal to 0, is the 0 solution. So the only solution to this equation is the 0 solution. So how do we show that? We solve this equation, and then I show you that the only weight that I can put here that make this is 0 is the 0 weight. So we solve this equation. So we take a nice piece of paper and we solve. So we need to solve the following equation. x1 v1 plus x2 v2 plus x3 v3 equal to 0. Now we do what exactly we've done before. It means x1 times 1, 2, 3. Those are my vectors. Plus x2. So that's the equation I need to solve. And I have to convince you the only way this can happen if that x1, x2 are equal to 0, plus x3 times 2, 1, 1 equal 0, 0, 0. That's the equation I need to solve. And I have to show you that the only solution is the 0. But solving this, as we've done several times, is actually boiling down to solve the following system. x1 plus 4x2 plus 2x3 equal to 0. x1 plus 4x2 plus 2x3 equal to 0. That's the first entry. 2x1 plus 5x2, so 2x1 plus 5x2 plus x3 equal to 0. And 3x1 plus 6 plus 1 equal to 0. And as you guys have noticed, this is the vector v1. Basically, this is the v2 and this is the v3. So we need to solve the system. All right, so we do what we always do when we solve those type of system. We go to the echelon form. And the only thing I'm interested in is the solution unique. Do we have only the 0 solution? So we go to the echelon form that I will not go through it with you. You guys should know by now how to do that. And after doing some operation, I ended up with that. 0, 1, 1, 0, 0, 0, 0, 1. So the question is the solution unique? So this is my 1, my leading, my leading. So if I solve here, do I get one solution or more than one? So let us solve this. The last one, obviously, the last one is x3 equal to 0. This one read x2 plus x3 equal to 0, but x3 is already equal to 0. So this is x2 equal to 0. And the first one tells me x1 plus 4x2 plus 2x3 equal to 0, x1 is equal to 0. So the only solution is the 0 solution. So since x1 equal x2 equal x3 equal to 0, by definition, the vectors are linearly independent. Okay. So linearly independent means that the only weight I can put here to make this sum the 0 vector are the 0 weight. Now we're going to move to dependent, which is going to help us exactly understand the concepts, definitely more than now. So we're going to do another problem where I'm going to ask you to show that they are linearly dependent, which is going to help us know what is really the idea behind here. Okay, can I move on, guys? Okay. So question number 2. I'm going to take 3 other vectors in R3. V1, V2, V3, and the question is, show that the vectors are linearly dependent. What does this mean? Linearly dependent. It means we have to show that. That's what we have to show. That the following equation, my red pen doesn't have ink anymore. We have to show that this equation plus x3v3 equal to 0, that's what we have to show, has a non-zero solution. It means we can find numbers, not zeros, that make this 0. Has a non-zero solution or a non-trivial solution. Another word for non-zero is not trivial solution. Okay. So the only way we know that is by solving this equation and ask ourselves, can I find non-zero scalars? So as we did before, it means that's the equation I need to solve. 1, 2, x3 plus 4, 5, 6 plus 2, 1, 0 equal 0, 0, 0. That's what I need to solve. So I'm going to put this in an augmented as usual and solve it. That's the only way we're solving so far, because if you read it, x1 plus 4x2 plus 2x3 equal to 0. So we are equating entries basically. And I reduce. And as usual, I will just give you the reduced form. And I don't need to go to the reduced echelon form because my question is, does it have a non-zero? I'm not really asking you basically to solve it at this stage. So I will stop at the echelon form. I'm going to get 0, 1, 1, 0. And I get 0, 0, 0. So this is a leading. This is a leading. That's what I get. So now my questions, does this equation have a non-zero solution? Yes or not? Can you find scalars, not zero, that will satisfy this equation? We solved. Now I know zero satisfies it. 0, 0, 0, 0. Are there non-zero solutions? Yes or no? Back to you. Can I find non-zero solution to satisfy this equation? What can you say? Yes? Okay, because. Absolutely yes, because. There is a free variable, of course. So here x3 is free. You can take any value you want. Since x3 is free, it means we have infinitely many solutions. Infinitely many. In particular, because what I want is a non-zero solution, in particular, so we have infinitely many, in particular, a non-zero solution. So they are linearly dependent. That's the definition. Okay, so if I can find a non-zero solution, it means the vectors, by definition, are linearly dependent. So in the linear independence, the only solution is the zero solution, which is forced me to have a leading basically in every column to have a uniqueness. Here, no, I want non-zero solution. The only way I can have non-zero, because 0 is already 1, is to have a free variable. Therefore, they are linearly dependent. Now, question 2 is, what does it tell us about those vectors? What does it tell us about the vectors? So my second question is the following. My second question is the following, which help us clarify the idea. My question is, find a linear dependence among the vectors. What does this mean to you? It means the following. Find a non-zero solution, that's crucial. That's what it means. Find a non-zero solution of this equation. So now I actually want you to solve. I want you to give me a non-zero solution. One, I don't want a lot of them. I want one non-zero solution and then substitute it back into this equation and then substitute the solution back into the equation. And now we do the work. Substitute the solution back into this equation. So find a linear dependence is actually, that's really what it means. And let's see why this helps us understand the concept. All right. I want to find a non-zero solution. So based on what I did previously, so it means when I try to solve that previously, then I ended up with the following matrix. 1, 4, 2, bunch of zeros, 0, 1, 1, bunch of zeros, 0, 0, 0, 0. Now I need to find, not all of them, I need to find one non-zero solution. So, okay, let us solve. If I solve, I have my x3 to be free. I have x2 to be 1 minus x3. And I want x1 is minus 4x2 minus 2x3. Remember, I'm not asking for a general solution. I want one non-zero solution. One, not all of them in this problem. Okay, so one non-zero solution is, and you have to give a value for x3, so you can give me anything you want. One non-zero, suppose I take x3 to be 1. Let me take x3 to be 2. I don't care, you can pick anything. X2 is 1 minus 2, 1 minus 2, minus 1. And what would be x1? What will be x1? Minus 4x2, it means it's a 4. 4 minus 4, okay. I get a 0. Okay. Is this making sense? I put x3 to be 2. This is going to be x2. So you pick anything for x3. And x1 is minus 4x2. It means minus minus, that's a 4. 4 minus 4, this is going to give me x1. So that's one possibility. But what does it mean to you? I feel there is something not correct here. I'm sorry. You guys should have corrected me. I knew that something is wrong. All right, so let us pick one solution. Sorry about that. I pick x3 to be a 2. x2 will be a minus 2. Now, actually, it makes sense. And then x1 would be minus 4 x2. It means minus 4 times minus 2, which is an 8. And then minus 4, which is going to give me a 4. Okay, and that's really, yes, yeah. So that's a solution, x1, x2, and x3. Now, what's a linear dependence relation? Once you find a non-zero solution, we plug it back into this equation. So this tells me that 4v1 minus 2v2 plus v3 equal to 0. So I find one of them and then plugging them for x1, x2. There are infinitely many, as you guys noticing. I picked one of them. But I saw a linear relation, it means that's the relation that exists between the vectors. So if they are linearly dependent, I can find those weights that help me to have this relationship between the vectors. Independent, there is no way I can find them. The only one that work here will be the 0 weight. That's really the importance of dependence. So now my question is, can you use this linear dependence relation to express one of the vectors as a combination of the other two? So now, that I found this relationship between them, can you express one of the vector as a combination of the other two? Yes or not? Now I find a relationship between them. That's what I talk about. Can I express one as a linear combination? What do you think? Yes, solve for one, absolutely. So because I can find those weights, I can solve for one. So I don't know, let us solve for V3. So 2V3 is minus 4V1 plus 2V2. It means that V3 is minus 2V1 plus V2. I was able to express one as a linear combination of the other. So let me a little bit summarize the definitions and what's the dependence versus independent. In the dependence case, because I was able to find non-zero numbers such that this hold, I was able to express one as a combination of the others. In the independent relationship, they are independent.
Theory 1-1.
If they are linearly independent, this means that there is no way I can find weight. No way I can find weight to make this expression equal to 0. There is nothing here Nothing here, only the zero weight, which is gonna stop me from expressing one as a combination of the others. That's really the idea of dependent versus independent. So let me take another question to understand more dependent, because once we understand dependent, we can understand independent. So characterization of linear dependent set. Suppose I give you the following question. I pick V1 to be 1, 2, 3, V2 to 4, 0. And V3, I'm gonna pick it in front of you because that's why I kept it empty. I'm gonna pick it to be, let us say, very simple, V1 plus V2, nothing really deep. So I'm gonna pick V3 to be 3, 6, and 3. Okay, I picked it. My question is, show that they are linearly dependent by finding weights, x1, x2, x3, not all zeros. That makes this sum equal to 0. So I'm giving you a scenario where I have two vectors and I pick one vector which is nothing more than their sum. It's a combination. And I'm telling you now, show me that they are linearly dependent in this particular scenario by making up weight. That makes this equation hold. Can we do that? So we have V3 to be V1 plus V2. And I want you to find the weight. So Dylan is telling me the following. Pick x1 to be 1. Pick x2 to be 2. And pick this one to be minus 1. Now, what did he base this on from? He took this relationship and he rewrote it basically as V1 plus V2 minus V3 equal to 0. So if I have one vector, if it's a linear combination of the other two, then I can easily find a non-zero relationship. I can easily find non-zero weight that makes this sum equal to 0, making the vectors linearly dependent. So, conclusion. Suppose we have a bunch of vectors in Rn. Then the vectors are linearly dependent if at least one of them is a linear combination of the other. This theorem is used only to understand the concept, not for algorithmic purposes, not to show linear dependence, but to understand it. So if you have a bunch of vectors, they are linearly dependent if at least one of them is a linear combination. Because based on the previous example, if I have 3 vectors, because V2, I was able to write it as a combination of V1 and V2, then I was able to find a non-zero solution for this. Therefore, they are linearly dependent. And if I can find a non-zero solution, I can move backward and solve for one in terms of the other. And the vectors are linearly independent, if none of them can be written as a combination of the other. None of them can be written as a linear combination. As a linear combination of the other vectors. All right? So, solving this equation will allow me clearly to check whether I can express one as a linear combination or I cannot. If I can find those non-zero, I can do it. If there is only one R0, there is no way I can do it. And that's what the linear independence is really telling us. There is no way I can get one as combination of the others. Do you have any questions before we proceed? Our goal is really to understand this concept the best we can today. Any questions? All right. So let us move a little bit to the geometric interpretation of linear independence versus dependence. What's a geometric interpretation? Okay. Let me take two vectors. In R2, it means they have two entries. In R3, they have three entries. What does it mean for two vectors to be dependent? Okay, so suppose you have two vectors, U and V. So we have a vector U. What does it mean, linearly dependent? Linearly dependent, if I follow the definition, it means we can find scalars, not zeros. We can find x1, x2, not both zeros, such that this equation is satisfied. That's what linearly dependent. It means I can find weight. If I solve this equation, the weight not both zero such that this hold. But now if I solve, let's see if x1 is non-zero. So if I can do that, I only have two vectors and I solve for V1. As we did before, this means that my vector V1 is going to be minus x2 V2. Remember, those are just a bunch of numbers divided by x1. So if they are linearly dependent, it means V1 is a scalar. So it means V1 is a scalar times V2. Okay. Yeah, we can scale. I don't know what you mean by intersect one another. That doesn't really make sense to me, but scale them. So what does it mean for two vectors to be linearly dependent? Dependent, crucial. Two vectors are linearly dependent if one of them is a scalar multiple of the others. That's if you have two vectors, whether it's R2 or it's R3 or anything, that's what it means to be linearly dependent. They have to be scalar multiple of each other. Independent, so two vectors, so now we can say two vectors are linearly, two vectors, the two is important here because that's hold for two. Two vectors are linearly dependent if they are scalar multiple of each other. Multiple of each other. They are linearly independent if this doesn't hold. They are linearly independent if they are not scalar multiple of each other. Not scalar multiple. It means you cannot get one by just stretching the other. Okay, so a very simple example. Now I'm going to take you two vectors and you have to tell me, are they dependent or independent? Only two vectors, not more than that, because otherwise it becomes fairly complicated. And so suppose I take the following two vectors, 2, 4, and I don't know, 4, 6. So geometrically, we're going to do this problem geometrically and algebraically. Okay, geometrically. Are those two vectors dependent or independent? What do you think? Okay, so let's consider those two vectors. So let U be the vector 2, 4. And V to the vector 4, 6. Okay, geometrically, and then I'll do it algebraically because most of the time we have to do it algebraically because you cannot do those things geometrically except simple stuff. Geometrically, are they linearly dependent or independent? Okay, from here to here, you multiply it by 2. But from here to here, definitely you're not multiplying by 2. So the question is linearly independent. The answer is no, because they are not scalar multiple of each other. There is no way, not scalar multiple. That's geometric. Now, algebraically. But as I said, most of the time we have to do them algebraically. How do we show them algebraically? Ask myself, I want to solve this equation. Ask myself, can I find weight, non-zero weight that make this equal to 0? We know no way, because if I can find them, I can write them as scalar multiple. But now still we're going to do it again. We're going to do it algebraically because we have to do it. So it means I'm asking myself, if I solve this system, this homogeneous system, so be very careful, that's a homogeneous system. Can I find non-zero? All right, so let us solve the system. Remember, 0, 0, that's the vector 0, 0. This vector has 2 entries because I'm adding vectors in R2. So this has to be in R2 vectors. 4, 6, 0, 0. Okay, we do that. 2, 4, 0. Minus 2, minus 4 plus 4, it's a 0. Minus 2 times 4, that's a minus 8. Minus 8 plus 2, which is a minus 2, and a 0. Now let us solve. Of course, we have a leading here and a leading here, so we expect a unique solution. So, but let us still do it. This row will read minus 2x2 equal to 0, which is give me immediately x2 equal to 0. The first one will give me 2x1 plus 4x2 equal to 0, but x2 is 0. It means x1 equal to 0. So we get x1 equal x2 equal to 0. It means linearly independent, because there is no way I can put any numbers here except the zeros to make this equal to 0. So that's algebraically and that's geometrically. So 2 vectors are simple, but that's basically about it. Otherwise, you know, it becomes way more complicated. But still, we have to understand a little bit the geometry. In case I have 3 vectors, geometrically, how can they be linearly dependent or independent? So let me take the case of 3 vectors at the pure geometrical stage. So let us say, and I want them in R3. I want them in R3. It means I am in 3 space. In R2, I will take after that. How can 3 vectors be to be dependent? How can they be to be independent? Okay. So we have 3 vectors. Let me call them U, V, W. Geometrically, what should be the picture for them to be dependent? What should be the picture for them to be independent? I'll start, and then this will hopefully make you start thinking yourself. Suppose I take, this is my U. So I am in 3 space. So in the background here, this is X1, sorry, this is X1, X2, and X3. Okay, because I am in R3. Suppose this is my vector U. And this is my V. So I'm taking a scenario. And this is my W. Okay, those are my vectors. Are those independent or dependent? What do we think is happening here? What do you think? Without any, it's a simple scenario. Will those be dependent or independent? Okay, somebody's telling me independent. Do you agree? Yes? Yes? Okay, we're in trouble. Okay, those are not. And let's see why they are not. Watch the picture carefully. Watch the picture very carefully. I picked my V on purpose to be what? Almost 2 times U. Means V is a combination of U, so it's 2U. Is that clear? Now I'm going back to you. Can you give me scalars? Can you give me non-zero scalars? Absolutely, absolutely. Can you give me non-zero scalars to make this sum equal to 0? Not all of them has to be non-zero. Can we give them? Based on this, if I put a 2 in here, and I put a -1 in here, and I put a 0 in here. Okay, I put a 0 in here, then this is equal to 0 because 2U minus V equal to 0. And the condition for linear dependent, I didn't say all of them has to be 0, at least one of them has to be non-zero. So those are absolutely linearly dependent. And now I go back to my characterization that a lot of you are writing it on the board. Characterization. Vectors are linearly dependent. If at least one of them, I didn't say every one of them, if at least one of them is a combination of the other, is a linear combination of the other. Which one is a linear combination of the other? The vector V is a combination of the vector U. It's basically 2U. So since one of them is a combination of the other, this really helped me to find those scalars that make the whole thing equal to 0. Absolutely linearly dependent because one of them is a linear combination of the other. That's the dependence. Okay, that's one scenario. So now another scenario. Another scenario. So actually, no. So this is my okay, this is again my R3, my background. And now I have my vectors. This is my U. I'm not changing my U. And this is my V. So now I did not put V as a scalar multiple of U. I dropped this condition. So those are not. And then my third vector W, I'm going to do it this way. I'm going to put it here. I'm going to look at this plane right there. So this is the plane. It's the plane that contains, so I'm going to call P the following. P is the plane. Is the plane that contain 0, contain this one, contain the vector U or the tip of U, and contain V. So this is my plane. In other words, if you remember, P is basically, I'm looking at the span of U and V. So V is the span of U and V. It means every possible linear combination. Now, suppose I take W in the plane. In other words, suppose I take W to be a linear combination of those. Are the vector U, V, W dependent? Okay, so suppose I take the W, what is my W here? So my W is, we can sketch it very easily, is 2U plus V. So that's my plane. It contains U. I stretch it. I'm still within it. Then I move the direction of V. I'm still within it. This is my W. Are those dependent or independent? Quickly. Absolutely dependent. those are dependent because W is a combination of that. That's the dependence picture. So if I go back to the definitions, all right, I again write 2U plus V minus W equal to 0. I can find those non-zero weight. This is because W is a linear combination. So now 3 vectors. What's the scenario so far? One scalar multiple of the other cause dependence. Okay, none of them is a scalar multiple, but one is a linear combination of the 2 others. This is linear dependence. So how can I break the linear dependence for 3 vectors? What shall I do? What shall I do? Geometrically, who would like to speak up? So geometrically, how can I stop 3 vectors from being linearly dependent? U has to be outside the plane, absolutely. So the only way I can stop it is to make U or V or W, one of them, I don't care which one, to make one outside the plane, which is formed by the other 2. So to have linear dependence, again, to have linear independence, I really want to, so this is my background. This is my X1, X2, and X3, because I am 3 vectors in R3. This is really the background. And these are my U and V, not scalar multiple. That's the plane which is formed by them. So it's my plane. I can see it. It go through U, it go through V. That's really the plane I'm thinking of. So the plane I'm thinking of is the span of them. So the plane I'm thinking of is nothing more than every linear combination of those 2 vectors because they are not scalar multiple, so their span is the plane. So my W has to be outside the plane. My W has to be here, so we can basically project it down into the plane. So that should be my W, and W not in the plane, not in the plane, not in the plane P. This is linear independence for 3 vectors. Okay, so 3 vectors in R3, and the word R3 is actually important here, and you will see that in a second, why R3 is important. So in R3, if you have 3 vectors, what's gonna happen? If one is a scalar dependent, if they all lie in the same plane, mean that I can express one of them as a combination of the other 2. That's what means lying in the same plane. Then they will be dependent. The only way they are linearly independent is they don't lie in the same plane. It means if I take the plane formed by U and V, W is outside it. If I take the plane formed by V and W, U has to be outside. And V has to be outside the plane formed by U and W. There is nothing, no way I can express one as the sum of each other. Okay, so that's the geometry for 3 vectors in R3. Now, once we hit R4, the geometry definitely become hard and only algebra will get into the picture. But, so now let me, I wanna treat 3 vectors in R2 clearly. So I'm gonna talk a little bit about special vectors. Okay. So I want to read the first question. I tell you that every set of vectors, so if I have a bunch of vectors, and if one of them is the 0 vector, okay, so I give you a bunch of vectors. Let me, suppose I give you like V1, V2, V3, and I plop in the 0 vector. So I have this collection, right? Immediately, this is linearly dependent. Okay, give me an argument. Who would like to give me an argument? So I have a bunch of vectors. One of them is the 0. Well, they are immediately linearly dependent. Doesn't have to be geometric anymore. But actually, I don't want it geometric. It's hard. I just want it basically algebraic. Why linearly dependent? Two reasons. First, if I think about in terms of the definition, I'm going to do it two ways. Suppose I solve this equation. Plus x4 times 0 equal to 0. Suppose I solve this, okay? Do you think I can get a non-zero solution without solving? Please, can you give me, wait, not all zeros, but the sum is zeros. Zero, 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 one. Is she correct? Remember, not all the way it has to be zero. So if I put 0 times V1 plus 0 times V2 plus 0 times V3 plus 1 times 0, I get 0. It means x1 equals 0, x2 equals 0, x3 equal to 0, but x4 equal to 1 will solve this. So I need an algebraic reason. Therefore, they are immediately linearly dependent. If you guys put those into a matrix, you're going to have a free variable. That's what's going to happen. Okay, so whenever you have a set, if one of the vectors is 0, immediately they are linearly dependent. Now, the more interesting case is this, and that's important. In the previous case, when I took 3 vectors, I kept telling you R3 is important. And let's see why. I'm stating a fact, the following. Any 3 vectors in R2 are linearly dependent. Means if I give you any 3 vectors, somehow you should be able to express one as a combination of the other. Let's see why this is the case. Why this is the case. Algebraically. Algebraically, because I want to generalize the algebra part. Algebraically. Why this is the case? Okay, suppose I have vectors V1, V2, V3, all of them in R3. Sorry, R2, crucial. Having R2 here is absolutely important. It's not R3, okay? And I want to convince you that they are linearly dependent, even though you don't know the entry of that. But how can I do that? To do that, it means I have to solve this equation. We have to solve this equal to 0. And I have to convince you somehow that when I solve it, I have a non-zero solution. So we have to solve this equation. Okay, now, when I solve this equation, let us see what should we get. Even though I don't know the entry, but we can actually figure it out. Every one of them has 2 entries. Entry here, entry here, entry here, entry here. Each one of them has 2 entries. So when I am going to solve, I need to take the augmented matrix that correspond to it. So what's going to be the augmented matrix? This is the V1 vector. This is the V2 vector. This is the V3 vector. And this is the 0 vector. That's the augmented matrix. And now I go back to you. So the system that corresponds to this matrix is a system of 2 equations with 3 unknowns. X1, X2, and X3. Another question to you. Are they dependent or independent? What can you say? It means, can I find a non-zero solution? Or I cannot find a non-zero solution. Even you don't know anything, but you know enough to be able to answer my question. So if we solve this system, are we going to have a non-zero solution? What do you think? That's a system of 2 equations with 3 unknowns. Okay. And this is definitely, that's a homogeneous system. It means we know there is one. My question, are we going to have more than one? So Valerie, you told me no, but I don't know no for what? Dependent or independent? Is there infinitely many or unique? Anybody? Are we going to have a non-zero solution? Yes or no? So if I solve the system, V3 can always be expressed as a linear of V1 or on single. I'm not going to pick up your answer, Dylan. I want an answer to my question. Does this system has a non-zero solution? Yes or no? That's my question. So does the system has a non-zero solution? That's what I want. That's the question I want. And I don't want the geometry yet. I want that. If I solve this, am I going to have a non-zero? Absolutely, we will have. Doesn't have to be, it's not V, doesn't have to be X3. Since I have a system, we have two equations. It means when I'm going to reduce, the maximum number of leading is going to be 2, because I have 2 rows, and the leading is the first entry in a row. So if I have 2 rows, it means I'm definitely going to have a free variable. So does the system has a non-zero solution? And the answer is absolutely yes. The answer is absolutely yes. Because since we have only 2 rows, so the maximum number of leading is going to be 2. I cannot have more than leading. So one of the variable is free. That's what's going to happen. So if I'm going to solve at max, I'm going to have 2 leadings. I don't know where they are going to be. So my leadings could be anywhere. I can have a leading here, 0. I can have a leading here and 0. But I can have at most 2. So one of the variable has to be free. It could be x2, it could be x3, and it could be x1. So one of the variable is free. It means we have a non-zero solution. We have a non-zero solution. So any 3 vectors in R2, any 3 vectors in R2, whenever I throw any 3 vectors in R2 are linearly dependent. What's causing this is that when we solved algebraically, when we solved 3 vectors in R2, it generated a system of 2 equations, the 2 equations because each one of them has 2 entries. And because I have 3 vectors, I have 3 unknown. So I have a system where the number of unknown is more than the number of equation. It's causing one of the variable to be free, x1, x2, x3. We don't know which one, but it means the vectors are linearly dependent. Okay. Now, I will explain the geometry in a little bit, but I would like to push that further. Suppose I give you the following. Is this true or false? Any 3 vectors, any 4 vectors in R3 are linearly dependent. Is this true or false? What can you say? Algebraically. 4 vectors in R3. So I have 4 vectors, V1, V2, V3, V4 in R3. Are they linearly dependent? Again, algebraically. If we try to solve the system, can I find a non-zero solution? Yes, again, it's the same logic, because this will generate a system of how many equations? If my vectors are in R3, each one of the vectors have 3 entries. So I'm going to end up with 3 equations. And I have 4 unknowns. And that's a homogeneous system. I don't have consistency issue. So I have 3 equations and 4 unknowns. It means I want to have at most 3 leaving. So at most 3 leading, it means at most 3 basic variables, leaving 1 free. Hence, I can find non-zero weight, which make those equal to 0, which is going to allow me to express one of them, I don't know which one, as a linear combination of the other. So in general, if I have more vectors in the space where the dimension, if the dimension of the space, like the number here, is less than the number of vectors, they will be linearly dependent. So let us say how we're going to write this. Any k vectors in Rn are, you don't have really to memorize it because I want you actually to see the picture, are linearly dependent if the number of vectors exceed the dimension, if k is bigger than n. So 4 vectors in R3 are linearly dependent. 5 vectors in R4 are linearly dependent, and so on and so forth. However, this will be my last question. What if I'd give you 3 vectors in R4? Can we say anything about them? Can we say anything about them? Actually, nothing. They could be dependent, they could be independent. I have no idea how they will behave. Algebraically, 3 vectors will generate a system of 4 equations because they have 4 entries and 3 unknowns. So they will generate this one. And in this case, anything can happen. We can have free, we can have not free, and so on and so forth. All right, I stop at this stage. Your exam, number 1, of course, is next Wednesday. It starts at 2, and you guys have at least an hour and a half to do it. And your review for the exam. So you guys review your quiz. Go over the homework that a lot of you, I have this feeling you're not doing, and you know the price will be dear for that. So go over your homework. The 2 quizzes, but the quizzes don't cover everything. And then on Brightspace, I have an old exam. So you will have an idea what kind of question I'm expecting you to be able to answer. And I have basically a review in the sense what are the main topics that you are responsible for. So please go over all this and do the homework that I will assign. Dependence and dependence will be heavily presented on your exam. So please do all the homework I will assign for next Monday, and we discuss everything you guys want me to discuss with you. All right. 1.7, absolutely, that's section 1.7. We skipped 1.6, that's section 1.7. Please do every homework I assign if you want to do well on your exam. All right. Okay, the time's up. Anybody has any question can stay. I will answer you.
Do we go on the Zoom during the exam, or do we
You
just?
will be on Zoom, absolutely. I will be with you. Okay. Okay. Yeah, I will be with you as like the quiz. You guys can ask me questions on chat. I'll answer you, and so on and so forth. Nothing changes. Okay, any other questions? It will go up 1.7 included. 1.7 included. What I did today is absolutely included, heavily also.
Professor, do you mind explaining the geometric reason for linear, I don't know, linearly, I don't know, how do you say it? Linearly independent?
Dependent.
Okay, in R3, that's the only one I was confused on.
Okay, the idea is that here, if two vectors are like this, and this is V, which is twice U, for example, and this is W. Okay, this type of picture. Those are linearly dependent. And this is based on the following idea, the following principle work. Vectors are linearly dependent, bunch of vectors, even more than 3, linearly dependent. That's not how you show them, but that's how you understand them. If at least one of them is a linear combination of the other. Combination of the other. Okay, if one of them is a linear combination of the others, then the vectors are linearly dependent. So in this scenario, we have V is 2U. Means the vector V is a combination of the vector V. And why they are dependent? Because if this is the case, then if I rewrite this like I can rewrite this like that. Does this make sense?
Yeah, okay.
So if I look at this equation now, x1u plus x2v plus x3w equal to 0. Can you give me a non-zero solution? Means can you give me numbers that I can plug in here, not all zeros, such that this is equal to 0, based on this piece? You can take x1 to be 2, x2 to be minus 1.
Can one of them be 0 or doesn't?
Yes, one of them can be 0.
So you could do x1 is 2, you could do x2 is -2, and then x3 is 0. No, that'll be
What?
You could do x1 to be 2, x2 to be -2, and then x3 to be 0.
Problem here. V is 2u. So it's that's V is 2u. It means 2u minus V equal to 0. I'm trying to rewrite this. I'm trying to rewrite in this particular scenario.
I'm sorry, my computer's frozen. I'm trying to.
Okay. Let's throw this away. Okay. Suppose I have, forget about the geometry for 1 minute. Are you with me? Suppose I give you two vectors, u and v. Okay. And I tell you that v is 2u. That's what I give you. And my question, are u and v dependent? Linearly dependent. It means, can you give me scalars? That's really what dependent. I'm going to go to definition because otherwise I will be messing you up. It means, can you give me scalar based on this relationship? Not 0, such that this is equal to 0. Can you give me the scalars?
Yeah, you could do x2 equals to 2 and then 1 for x1, correct?
Right, you can do x2 to be what?
2.
2.
And then x1 to be 1.
No. It will not satisfy that.
Wait.
V equal to u. So this means 2u minus v is equal to 0, right?
Okay. Oh, okay, I see. You just
You
rearranged
see
it.
it now? What's the x2 now? x2 is 2. What's it? Sorry. x1 is 2. What's x2? Minus 1.
Minus 1.
That's the x1. x2 is the coefficient of minus v. So I have a solution which is not the zero solution. So they are linearly dependent. Let's take another example. Okay, still simple, still simple. So I'm going to imitate that. Suppose I take v to be half u. Are those dependent? Means, can you find scalar that I can put here, non-zero, that make this to be the zero vector? And what are they?
You could do 2 for u and 2 for x1, sorry, and then 1 for v, right? Or x2, I'm sorry.
I don't know. I mean, let's imitate that. So this is gonna one way, v minus a half u equal to 0. Correct?
Yeah.
So what's gonna be v? 1
Mm-hmm.
minus a half. So I have a non-zero solution. It means
Okay.
they are dependent.
Okay, I see.
Are you with me?
Yeah.
Okay, another example. Now I'm going to introduce 3 vectors, u, v, w. I'm going to take u, v, and w. I'm going to put it as 2u plus v. You know, it's a combination of both of them, a linear combination of both of them. Are the vectors linearly dependent? It means the same
Yeah.
question again.
Yeah, they are.
Give me the weight. I want the weight that are not all zeros that solve this equation. What will be the weight?
So minus 2u, correct?
Minus 2u, whatever you want. I mean, you give them to me and I'll make sure that you got them right.
And then minus 1v,
Minus 1v,
and then just 1 in front of
1.
w.
That's a non-zero solution.
Okay.
So according to our definitions, they are linearly dependent.
Okay.
Okay? So in general, I can actually kind of generalize this as much as you want. In other words, so if I have 3 vectors, if one is a combination of the other 2, they are dependent. That's how we understand it.
Okay, I see.
Okay, that's how we understand. That's not how we show it if I have numbers. You have really to go through the algorithm. So will this extend to 4 vectors? Suppose I have uv, I have w to be 2u plus, I don't know, plus 5v, and I have another vector. Let me make up another vector, z. Then I have 4 vectors, okay? My question to you, are those linearly dependent or independent?
Those are dependent, linearly
Because
dependent.
I want the weight. Because I want to make sure that that's what my definition is. And we're trying to understand the definition.
So it would be minus 2u,
Minus,
minus 2u,
yeah,
minus 5v, 1w, and would it be 0 for z?
it has to.
Yeah.
It has to. Because the condition is a non-zero, not all of the weight are 0.
Okay.
I didn't say the condition is every one of them has to be not 0.
Okay.
One is not 0, we are safe. So they
Okay.
are linearly dependent. So the rule in general is the following. That's how we understand, as I repeat, that's how we understand it. And what do I mean by that? It means if I give you numbers, 1, 2, 3, 4, 5, 6, 7, 8, 9, for vectors, and I ask you, are they dependent or independent? You have to use the algorithm. It means you really have to solve. This is to really make meaning out of it, to really grasp it. So,
Okay, I see now.
you see what I'm talking about? So now let us understand this. So
Yeah.
it means that if you have a bunch of vectors, if at least one of them is a combination, is a linear combination of the others, then they are immediately linearly dependent. Does this make sense now?
Okay.
That's the picture.
Yeah.
If one of them is a linear combination, at least one, not all of them. Z is not. I don't know what Z is. I'm just dropping it in here. If at least one of them is a linear combination, then they are immediately linearly dependent because I can have those non-zero solutions. Okay? Linearly independent, it means there is no way I can express one as a combination of the other. I mean, they are totally independent. Did you follow me here?
Yeah, I understand.
Now the geometry is falling into this idea. So now that's my geometry. I have this vector in R3 and this one here and W here. Are those vectors dependent or independent?
They would be linearly dependent
Because
U and V, they're scalars of each other.
it means that V is a combination of U, basically.
Yeah.
Okay, now scenario number 2. I took U here, so that's my 0, and I took my V in here. Okay, and my W, I was careful with it. I said, I'm gonna take the plane, this plane, that actually contain those. You understand what I mean by it contain them?
Yeah.
Okay, it contains 0, it contains U, it contains V. 3 points form a plane. Okay, and then I take a third vector. I call it W, but I take it inside this plane, right there, for example. Okay, now what do we know? We know that something that we've talked about several times, that if we have this vector inside the plane, I can write it as a combination of U and V. Because the idea is that if you have those two directions and you want to go to W, so you are in the same plane now. So imagine you have really a plane. Okay, it doesn't have to be the XY plane, any plane. And you have two different directions in this plane. And you have a third vector. Can you get from here to here following the U and V direction? Can you stretch U a little bit and V a little bit so you can get to U?
To get to U?
To get to W, sorry.
Oh, okay. Yeah.
Yeah, you can go a little bit here and then somewhere like this. So I mean, I just drew it in an arbitrary way. Yeah, somewhere like this. And you hit W.
Yeah.
If I take anything else, in fact, I can take like a W here. As long as I am in the plane, I am really safe because this is my W. I can go tiny bit this way. And then at some point, I want to move this way. Okay?
Okay.
So it means that if this W is within the plane, this plane, it means that this W could be written as a combination of U and V. Okay?
Okay. Yeah.
Are the vectors now linearly dependent or independent?
They would be dependent.
Absolutely. All right?
Okay.
What is the
understand.
last scenario that I took? Do you remember?
Let me see.
You remember what was my last scenario?
Was it in R4? Is that
No, no. I was working in R3. No, I cannot draw R4. I don't even pretend to. What are the other three vectors I took? I took Q and I took V. Okay? And I took the plane.
Oh, was it when W was outside of the plane? Is that the last?
Right. And I took W right here.
Okay.
So it's projected. I did this to tell you that it's outside the plane. There is something, it's not within the plane. Okay, so here is scenario, U and V are not scalar, they are like this, and W is outside the plane.
Okay.
This W, there is no way you can write as a combination of U and V. No way. Because if you, any combination of U and V, it means C1U plus C2V is obtained this way. You take Q, you stretch, you stay within the plane, you don't leave it. Then you go in the direction of V, you stay within the plane. So every combination leave you in the plane. So W is not a combination of U and V, no way. U also is not a combination and V is not also a combination. This is the picture where the three vectors are linearly independent.
Okay.
This a little bit better?
Yeah, I understand now.
Yeah, so this is the geometry, as I said. The algebra, most of the problem are done algebraically because, you know, once I put numbers, you have no idea where I am. Okay, so we cannot do that. But that's a geometry which is important to understand this concept. Otherwise, you know, it will be jumble mumble in your head. Now, if I give you numbers, you know, for the vector, which I will, you know, I give you a lot of problems for Monday. So you guys do them and then you start getting algebraically how to do it. It's just a matter of setting up the right matrix and asking yourself, do we have only the zero solution or we have a non-zero solution? Which is really boils down, is there a free variable or there is no free variable? Okay. Any other questions?
Oh, that was it. Thanks.
Okay, anybody else? Now who I was talking to, Matthew or Chris? Because I know it's not Max. What?
This is Mateo.
This is Mateo. Okay. Chris, do you have any questions?
Actually, I think you might have answered them, but when you were talking to Mateo, but I would like to just reaffirm something. So, when you're trying to find the weights
Yes.
for the linearly dependent equation, you go by the coefficients of U, V, and W, and you just line them up. U plus V plus W equal to vector 0 or minus whatever the signs are, and you just
Can you speak up a little bit, Chris?
Okay, I'm sorry. So the way you, in a linearly dependent vector equation, you just take, algebraically put U, V, and W all on one side, and then just
yeah, let's say this one. These are my vectors. Okay, I'm not gonna do the math because when I just plug in vector, I don't know how hard the math is. So if I wanna check them, linearly dependent or independent, I solve this. Okay?
okay.
All right. Now, depending on the solution and see what we get. So suppose I solve that. And you know how I go to the augmented, right?
Yes.
Yes. So basically, I'm reading off. Actually, I'm really reading this. X1 plus 3, X2 plus 6, X3. So I'm going to get 1, 2, 3 here, 3, 4, 5, and 6, 9, 7, and bunch of zeros, okay?
Okay.
And then I have to go to the echelon form to see are there non-zero solution. So let's see if we have non-zero solution here. Is there a quick way? Let me find a quick way to get that. Okay, I'm just finding the echelon form in a quick way. I mean, calculator way, that's what I'm saying. Okay, so we have 1, 3, 6, and 2, 4, and 9. 9, wait, yeah, 9. So give me a minute, I'm almost there. 3, 5, and 7. Here I am, and submit. And oh, okay, that's not great. 697, 4%. Okay. All right, so if I did that, I got this. Okay, now what does this tell me? Dependent or independent? Chris, are you with me?
Yes, I'm here.
Okay, what can you say? Do we have non-zero weight or the only solution are the zero weight?
I'm sorry. I have to.
What is it?
It's. I could just guess. Independent. No, dependent.
Why?
Because you have the unique solution there, and there's no free variables.
Okay, it means independent. Okay, the only solution is x3 equal to 0, x2 0, x1 0. It means independent. All right?
Oh, that's yeah, because
What?
everything. That's why I'm sorry. I forgot that part.
Yeah, it's independent. If the only solution are independent. However, if I kind of change those factors a little bit, okay, I'm gonna change them tiny bit. So I'm gonna take 1, 2, 3, and I'm gonna take 3, 4, 5, and I'm gonna take, for example, those vectors. Okay, I just change them a little bit. And the questions are not dependent or independent. So we have to solve and ask ourselves, do we have a non-zero solution? Okay?
Okay.
So I put this. And I solve. Okay, so because let me get it out of a calculator instead of me doing it. 1, 2, 3, 4, 5. So 5. I hope I didn't mess up too much the numbers. So, and the last one I put is 11 here. Okay. All right, so I got the following: 1, 0, 2, and 0, 1, 1, 0, 0, 0. Okay?
Okay.
All right, that's what I got just using a calculator. So what does this mean? Dependent or independent?
I'm sorry. What would they get? For some reason, I can't remember the conditions.
What?
happened? For some reason, I can't remember the conditions for linear.
Okay, independent, it means the only solution is 0, 0, 0.
Okay.
It means there is no free variable.
All right.
Dependent, it means we have a non-zero solution. It means we have a free variable. All right? But you have to study it till it becomes, clear in your mind. Are you with me now?
Yes. Yes.
So those are, since x3 is free, what does this mean? Means you can take any value I want. So if I can
Yes.
give x3 to be the value 1, 2, 3, and every time I pick x3, I have a different value for x2 and a different value for x1. So since
Okay.
x3 is free, we have a lot of solution, in particular a non-zero one. All right? So
Yeah,
because
yeah,
I
I'm
have
sorry,
a
what-
free, it means I have non-zero solution.
Okay. All right. Yeah,
Are you with
I
me
got it.
still?
yes. What is that? What is this? What does this say? X3 free. We have what?
Infinitely many.
Oh, okay.
Infinitely many solution, in particular a non-zero solution.
Okay. I got it now.
Okay?
Yes. That's it. Thank you.
Right? All right. Go over them and make sure you can shoot me email if you don't understand, or come to my office on Monday, anything that gets you through. All right?
Okay. Thank you very much.
Sure. Bye-bye.